Okay, so I'm going to make a couple of videos on controls of mechanical motion of mechanical systems. And I want to start off simple. We're going to just do a single pendulum. Okay, and you'll see I set it up so that that kind of hinge connection, you can see it right there, the green thing, that's a motor. It'll come in as a motor, and when we bring it into Simulink, and therefore we're going to be able to control the torque that we'll deliver to it. There'll be a port for that. So we bring it in the way we've been doing these, with this. Let's see, motion model, motion results. Sorry, that will export the Simwise XML. So let's go over to Simulink. There's that XML right there, and we will use our app called X Mechanics, and it's just select on that XML file. That launches the process, creates the Simulink model, and it does this nice thing of essentially packaging it through a MATLAB project, which among many other benefits of this means that I can put it all together and send it to you very rapidly. So anyways, here we are inside Simulink. Let's hit the space bar. Let's hit the run button. Pause it. Look at it isometrically. And we'll see essentially, it's that horizontal kind of initial position with gravity acting on its driving the motion completely. No actuation at all yet. All right, and I'm going to kind of do a Simulink thing, and that's going to be, actually I'm going to do a couple of Simulink things. All right, so I'm going to drag this down like this, right, and hit spacebar, right, and this bottom one I am going to configure. So instead of sending torque in, we are going to send in a motion profile. All right. You'll see it even renames that port motion_PVA. Hence, it's looking for one of these signals, and we'll use the smooth transition signal pretty soon, which will describe position versus time, velocity, and acceleration versus time as well. All right. So here's kind of the Simulink thing, which is you put things into subsystems. Put them both in. And top one I'm going to call, let's just call it pendulum. And this bottom one I'm going to call inverse dynamics. All right. And the idea inverse is, well, forward really is you apply forces, things move. You don't really have the ability in general to make things move and create forces, but this block does, right? And so think of it more as an analysis, right? But anyways, let's kind of go inside. A few things I want to do here. Give myself a little bit of space. All right, and so we want to measure the angle, right? And because it, X Mechanics detected that this was a motor, it not only set up those input ports for us, but also makes measurements on the motor, and it puts them in what we call the bus. So with this bus selector, it can detect all that information. It happens to be motion, torque, speed, and power, but we want motion right now. All right. Okay. And motion is one of those PVA things, right? Which means it's really a three-component signal composed of the position, velocity, and acceleration. And so, kind of knowing that there are three components, we just tell it, here, give me the first one. Right, and so now we got an angle. It's selecting off that first whatever port right there. All right, and the last thing we're going to do, and units are important, and so we're going to just handle it pretty simply here with a gain block. I'm going to set this equal to 180 divided by, multiply, divided by pi. Okay, and what it means is by default we're measuring angle in radians, but in this example I think it's much more convenient to express it in degrees, and we achieve that by introducing that gain like that. It multiplies that signal. And I think I'll go here now and change the name of that output signal to angle. Okay, that looks pretty good. All right, this one's going to be a little simpler, and that's because torque is torque, and we like the default units, and so we'll just go get a bus selector here. And select torque. Okay. All right, and I am going to comment that out for a little bit. All right, and I really want to just get to work on controls, and we're going to use a PID controller, and we're going to use feedback and all kinds of good stuff here. And so I'm going to type in PID, and we get it right there. All right, and I'm going to use the Simulink browser to just get kind of the rest of it. It's a little easier because all this stuff exists in the commonly used blocks, and so we'll get a constant. So a little more space this time. All right, and scope and a sum. All right. And so the basic idea of PID is to compare to a command signal. And so we'll put in 45 degrees for our command, and we'll take the difference between what we're commanding and what we're measuring. So let's send the measurement into the scope, but let's also feed it back, and that the signal the PID really wants is what we call the error, and therefore it's the difference between the command and the feedback. So I'll put a minus sign right there. All right, so that's our PID. Okay. So let's maybe I'll run it from the scope here. All right, and you know, first of all, it's simulation, but I don't worry about this too much at this point. I want to show you what we're looking at. That's an unstable response. But one of the really important points about mechanical motion control is your controller needs to understand at some level what it's controlling. All right, and so even PIDs with feedback operate with an understanding, and it's through what we call tuning that they do this. So it's an empirical kind of understanding that will get expressed in the constants that drive the algorithm. And so maybe at some point I'll do a video completely on PID, but I'll rely a little bit on previous knowledge for those watching this, as well as that there's loads of good videos out there, loads of great books, and the method is just classic, and it's got a tremendous legacy. But anyways, to kind of tap into kind of what I'll call the empirical understanding, we click on this tune button. Right. And so, what's in all those textbooks and probably a lot of stuff that's in those videos, well, it's been automated beautifully by MathWorks through this tool. All right. And right out of the, I'm going to have to, again, do this little move trick. Try drag it down there. It gives us a response, and it tells us that this is the tuned response, which means it chose the parameter values for us right there, right? And might be good, but you know, let's run it inside Simulink and see if that really did work out. So by clicking on Update Block, you'll see those numbers were automatically, just keep that out of the way right now, were automatically applied. I click on OK. I'm going to leave that open. We'll come back to it because I can assure you its first shot did not work that well. And so we'll hit Run again. Okay. And I'd say that this is perhaps the automatic tuning trying to be a little bit conservative, a little bit cautious, but it was not strong enough. And it's kind of getting into, again, this point that the better you understand the mechanics, the better your controller will work. All right. And we're going to do a few things to just kind of strengthen this, but I'll just kind of point out that the linear control approach, which is based on one data point, with regard to time, and that's t equals 0. It's called the operating point, about which a linearization takes place. And certainly, even the simplest of mechanical problems typically are not linear. Right? That's an issue that we're kind of contending with right now too. But I'd still say we can kind of get there, right? And that the method is still used so well because these things really do work. And so what I like to do is I definitely like to have this open as I do this. These are kind of the metrics that it gives us very quickly too, which are going to be things like overshoot. You can kind of see that one right here. That's probably about 0.1. More than that. That's 1.2. So that's about 0.1. 1.14 is the overshoot value. Yeah, and you could kind of look at this and see it yourself. Rise time, settling time, all kinds of stuff. And they use this term faster and I interpret it to mean stronger. But notice the numbers will change as I make it faster. And we just went from 14 seconds to 1.4 seconds on the settling time. And maybe I'll do it one more time. And these things look like they'll work pretty well. All right. And so update the block with the new values. And let's bring it up at this level. And let's run it again. And that looks pretty good. Right. And absolutely there's an overshoot. And perhaps that might bother you a little bit, but it probably doesn't if you're really working on a problem the way I am, because we basically made an impossible request. We said at t equals 0, we know your current angle happens to be 0, and we're telling you we want it to be 45. And so it's a remarkable thing that PID algorithms can interpret that impossible request and give you what is quite often quite reasonable. But whether or not it's reasonable to you really depends on what your machine's trying to do and what your requirements will be. All right, and so all I really want to do right now is address that impossible request. Right, and that in a way I'd say be careful allowing that PID to do that remarkable thing, which is interpret quite reasonably the impossible request. So let's go here. Let's get to my PVA stuff. So Terry's electrical and mechanical components, motion signals. There it is, smooth step position. Okay. And let's do something like this. At t equals 1 second, Let's take the next 2 seconds and let's go from 0 to 45. And so I'll delete that. I need to get one of my selector blocks. Okay, so we have that big overshoot right there. Looks like it's probably about 7 degrees. And very minimal, if any, overshoot right there. Got an interesting little lag right there. And again, I might save this for a video much more dedicated to PID algorithms, but that I is kind of the systematic corrector, and it's really kind of the integration of that error builds up the force, or what's in this example, torque, that would prevent it from ever sagging. Right, so let's not worry about that right now. I'm much more interested in what's happening up here at the top. Right, so that looks pretty good, right on 45. Probably something I should have been doing. Let's see. Okay, and we'll run it one more time. Yeah, so that looks beautiful. All right. So what's kind of cool about these smooth step transitions is, well, you can start to make them look more like step responses, right? And so let's put in a value, let's say 0.1. All right. So for simple mechanical linkage like that, I'm sure that's very much in the realm of reality of how fast they want to move something like that. All right. And basically, here's what your PID algorithm will give you. Right. And so it's because of that very strong, I'll call it gradient or whatever you want to call it, but really, rapid acceleration, it has a much bigger overshoot. So I think here's where I want to start introducing, again, this idea of more mechanics-based control. So let's kind of redecorate a little bit. Right. And I think I'll bring this down. And let's bring this up. And let's carve out a little bit of real estate for ourselves. Right. And what's kind of cool, we've already perhaps seen this in a number of videos I've done, is that we know how to calculate the perfect torque. So we're going to right? We actually even have the trajectory already set up for us right there. So all we really need to do is get an add block. Put that in place. Set that up like that. Set this up like this. Okay. Hit my space bar. And let's watch it from here. Oops. Okay. Units are important. Control C. And this needs to take that, well, let's just paste it in. Right. So that signal, and instead of multiplying it by 180 over pi, this time it will be Control X that. We need to convert degrees to radians. Okay, and let's try that one more time. And so isn't that beautiful? So I forget what the amount was, but it's probably 3 or 4, maybe even 5 degrees overshoot. That cleaned up the problem completely. And it's interesting to kind of look at these comparisons head to head. It's that basic idea that whenever you're applying feedback, you have to wait for the error to occur before the feedback mechanism does anything. You know that, again, PID is starting point is the error, and it takes the proper ratio of proportional, integral, and derivative actions on that error to come up with a ideal torque response. So I think I'll kind of wrap up this video at this point, and I'm going to do at least 2 more on this kind of basic idea. All right, thanks for watching.